Today we're going to talk about measures of spread. We're going to try to figure out how to talk intelligently about how spread out our data is. So here's our scenario. Chifaru is in charge of her study group. There's going to be 6 people in this group. And they're going to take a morning class and an afternoon class. And their scores on the midterm tests in the morning class are between 76 and 85. And then the afternoon class are between 65 and 97. If we look at our basic statistics that we have so far, the means and medians of these two sets are pretty similar. The morning class, the mean is 80 and the median is 80. And then the afternoon class, the mean is 79.5 and 78.5. So the means in the morning and afternoon, medians in the morning and afternoon are pretty similar, but there is something fundamentally different about these data sets. In the morning class, there's only 9 points separating the lowest performing person in the study group and the highest performing person in the study group, whereas in the afternoon class, there's 32 points in between the low and the high. So the means and the medians, they don't tell us the whole story about the data sets. There's fundamental differences beyond just where the centers are. So we need to come up with a decent way of talking about how spread out our data sets are, and do it in a way that is consistent and allows us to do some calculations, right? And allow us to tell us something about what's going on. So the first thing that we could do is we could see that there's a pretty big difference between the smallest and largest points in our data set. So the most straightforward thing we can do is calculate what's called the range of the data. The range in our case is simply the largest value of the data set minus the smallest value of the data set. And for our two data sets, in the morning our lowest is 76. Our largest is 85. In the afternoon, the smallest is 65 and the highest is 97. So in the morning, the range is 9 points. In the afternoon, the range is 32 points. And this is certainly a really nice, easy difference. But even if it is quick and easy to compute, it really only tells us something about 2 data points in our data set, right? Only the smallest point and the highest point. It doesn't tell us anything about the data points in the middle. And if we really want to talk about the spread of the whole data set, we need to figure out some way of saying something about where every data point is in relationship to every other data point. Fortunately for us, we've already calculated a statistic, the mean, that takes into account all of the data values. And so we simply use that as our center with which to measure all of the other data points by. And just as a quick notation thing, we call the deviation of any particular data point the difference between that data point and the mean. The statistics that we want to use that actually does this calculation is called the standard deviation. And I'm going to do an example of calculating a standard deviation in a separate video. There's a bunch of steps. It takes a little while to do. But what the standard deviation is, it's a single number that has the same units of our data, and it tells us something about how spread out the entire data set is. Okay, so this is the thing that actually does our work for us. And what the standard deviation does is, if the larger the standard deviation is, the more spread out the data is, and the smaller the standard deviation is, the more compact the data is, right? We might have spread out data here and compact data here. So just knowing those 2 facts, which class, the morning class or the afternoon class, would you think would have the higher standard deviation? Right? Which one has more spread out data? Right? Hit pause, think about it, and then we'll show you the process of how to do this next. If we want to calculate a standard deviation by hand, what we usually end up doing first is calculating what's called a variance. And then the standard deviation is just the square root of the variance. If we have data for the entire population, like Chifaru's study group, right? She has the midterm scores for all 6 people in her study group. So she can calculate the population variance. Right? To do that, we follow the following steps. First, we compute the population mean. Right? We've already done this for this data set, so step 1 is already done. Step 2, we calculate the deviation for every data point. So we'll calculate this difference for all 6 data points in our data set. Then for each one of these deviations, we take it and we square it. Then we add up all of those squared deviations, right? This symbol here is the sum symbol. That means to add them up. And since we have the data for the entire population, right, we are only interested in the study group right now, we divide by the total number of data points. And so in this case, we would divide by 6. And that final number is our population variance. In math, we can actually compactly write steps 2 through 5, right? The variance is going to be equal to the sum of the squares of the deviations divided by the total number of data points. And at last, our standard deviation is simply the square root of the variance. I'll probably end up saying this a lot. Once we get the variance, the standard deviation is the square root of the variance. You'll notice that there's even a little hint in our notation. The variance is sigma squared, so taking the square root of a square, that gives us the number that we're after. Right? So the standard deviation for the population uses the symbol sigma. If you follow through the process with our morning class and afternoon class information, we get that the standard deviation for the morning class is 3.06. The standard deviation for the afternoon class is 10.98. These are standard calculations that show up if you use a statistical analysis on your calculator in SPSS. This is simply part of our descriptive statistics. If we only have data for a sample, right? So if we treated Chifaru's study group as a sample for the entire class that these people are in, then it's only a sample. We only have 6 data points of the maybe 100 data points we have total. The calculation of the mean is the same, but it uses the symbol x bar instead of mu. And the calculation for the standard deviation is slightly different, and I'll show you exactly where those differences are. The first couple steps to get the sample variance and the sample standard deviation are the same, right? We calculate our mean. Since we don't have all the data, we can't use the Greek letter mu. That's set aside for having the entire population data. We calculate our deviations, we square them, and then we add them up. Now the last step is where the difference occurs. To get our sample variance, we divide the result by 1 less than the number of data points. So if we have 6 data points, we would divide by 5. If we had 20 data points in our sample, we would divide by 19. This is because if we only have a sample, we tend not to capture all of the variability of the data set. And there's a lot more elegant ways of doing this, but this works really, really well, and it's really, really simple, which is a pretty good combination. So if we divide by n minus 1, we get a pretty good estimate for the population variance, right? So this is just going to be a sample variance, which is an estimate for the population. In our symbol 1 statement for steps 2 through 5, S squared, which is going to be our sample variance symbol, right? It's the sum of the squares of the differences divided by 1 less than the number of data points. So if it's a sample, we divide by 1 less than the number of data points. If we have the population, we simply divide by the total number of data points. And to get the standard deviation for the sample, S, we simply take the square root of the variance.